A flame is a visible manifestation of combustion process, specifically the rapid oxidation of fuel in the presence of an oxidizing agent like oxygen. This chemical reaction is exothermic, meaning it releases energy, primarily in the form of heat and light. The combustion of the hydrocarbon, which are commonly found in fuel like natural gas, gasoline, and wood, produces water and carbon dioxide as a primary byproduct, both initially in an excited state. So this equation, as you can see, this is the hydrocarbon and this is reacting with the oxygen to produce carbon dioxide and water vapor. As these excited molecules return to their original stable low energy states, they release energy in the form of photons, which are particles of light. This photon emission occurs at specific wavelengths, which are characteristics of the molecules involved. So, excited H2O releases photon or releases energy and goes back to stable low energy state. Similarly, excited carbon dioxide releases photon to be in the stable state. The emission spectrum of flames. Emission spectrum of a flame is a key indicator of its combustion characteristics and can be used to identify the type of fuel is being burned. This spectrum includes several distinct bands. So this is a fire spectrum. In the y-axis we have relative intensity and the x-axis we have wavelength here, right? And if you see this fire spectrum, there is a bump in the UV radiation initially at around 200 nanometer, right? So this particular emission or this particular radiation in the UV spectrum, this is usually associated with the high energy process that occurred during the initial stage of the combustion. So this is obviously typically associated with the type of the fuel, what kind of fuel you are using, it will be associated with that. The most prominent part of the emission spectrum falls within the range of the zero point 0.4 to 3 microns, which includes both visible and IR spectrum. The intensity and exact wavelength distribution within this range can vary significantly depending the chemical composition of the fuel and the combustion conditions. So in case of this hydrocarbon, you will mostly see there will be some peaks between 2.5 to 3. This is due to the water vapor, and there will be something from 3.8 to around 5.5, and this is because of the emission from the carbon dioxide molecule. So if it is a non-hydrocarbon where the chances of forming of CO2 is not there, you will only see this particular peak, not this peak. This peak will be absent there. So this peak will be absent in case of the non-hydrocarbon. There are mainly 5 different type of fire detector available in the market. They are known as IR detector, UV detector, UV-IR combined detector, UV-IR square combined detector, and multi-IR detector. Ultraviolet detectors are designed to detect the UV radiation with wavelengths below 300 nanometer, which falls within the solar blind region. These detectors use phototube that includes a anode and a cathode. As you can see in the picture, there there is an anode and there is a cathode here, which are separated by a potential differences of around 300 volt in a sealed quartz tube filled with inert gas. The- when the UV photons strike the cathode, electrons are released and drawn towards the anode, ionizing the gas molecules and creating a chain reaction that generate an output signal in the form of the current. UV detectors are normally used for detecting flammable liquid fire such as hydrocarbon fire, but also they are very effective for metal fire, ammonia, or hydrogen fire. They offer rapid response, often in the hundred of milliseconds or less, and achieve high sensitivity level. However, their effectiveness can be reduced by the presence of smoke and factors such as oily flames or other organic compounds on the detector window can limit their sensitivity. UV detectors are also prone to false alarm caused by lightning, electric arcs, or X-rays. So with respect to advantages, there are mainly two advantages. They are response very quickly in the millisecond and have very high sensitivity in the range of picowatt per centimeter square. With respect to the disadvantages, the presence of smoke attenuates the signal. So in the flames where there is a chance of presence of smoke, UV detector cannot be used. Presence of oily film on the sensor window. So there is a sensor window here. So over the period of the time, there can be accumulation of oily flames, or during the fire itself, there can be accumulation of oily flames, and that affects the UV radiation to pass through the window to the ionization chamber, right? And that results in faulty reading. False alarm can be triggered by external influences like lightning storms, electric arc, or X-rays because they also belong to that UV radiation range. So there is a chance of false reading from them. Infrared detector or IR detectors operate by detecting the thermal radiation and particularly sensitive to the variation in the received light signal. These detectors use sensor, pyroelectric sensor with tantalum or lithium crystal coupled with operational amplifier and field effect transistor. An optical filter filters out spectral bands of the wavelengths which are 2.9 micrometer and 4.3 micrometer and 4 to 5 micrometer. So 2.9 is specific to H2O vapor and 4.3 to 4 to 5 micrometer they are of CO2. So IR detector captures the random flickering of flames in the infrared band, generating a signal that is processed by a low frequency bandpass filter before being interpreted by the microprocessor. Modern IR detectors have high signal to noise ratio, enabling significant amplification and excellent sensitivity to the flame radiation. They perform well in the smoky environments and low burn rate fires, but are sensitive to aqueous environment and other IR interfering sources. To enhance their performance and reduce false alarm, multi-IR configuration are often preferred. With respect to the advantages, IR detector perform well in the smoky environment and in scenarios involving low burn rate fires, such as gas oil. Compared to UV detectors, IR detectors generally offer greater reliability and longer mean time between failure. And disadvantages is they are sensitive to aqueous environments like frost, fog, and other IR interfering sources present in the surrounding. UV-IR combined detectors integrate both the technology of UV and IR using a AND logic gate, which means that if your fire is detected by UV channel and fire is detected by IR channel, then only there will be an output. If one of the channel does not detect the fire, then there will be no output. So in this process, the advantages are there are excellent rejection of the false alarm because we have used a AND gate, and when only the both the channels are giving the positive result, then there will be output. And good detection distance. It is not excellent but good. And disadvantages are UV IR combined detectors suffer from the combined limitation of the IR detectors. So both detectors have some disadvantages like UV cannot detect in the smoky environment, IR cannot detect in an aqueous environment of fog and frost. So both these disadvantages are there in the UV IR combined detector. UV R square combined detector represents a advanced iteration of the UV-IR combination, incorporating an additional IR sensor to enhance the detection capabilities. While the detection range is still limited by the infrared component, second IR sensor provides an extra data that boosts the gain in the detector amplification chains. This is not only extends the detection range but also maintains a strong immunity to the false alarm. This makes UV-IR square detectors particularly effective in the environment with complex fire detection needs. So in this kind of detector there is one UV channel and two IR channel. As a result, there are more amplification and it is able to cover more distance compared to only UV IR detector. With respect to the advantages, obviously it has enhanced detection range and more improved immunity to the false alarm. With respect to the disadvantages, despite the improvement, the detection range is still limited by the infrared components, which may not be suitable for all applications, and higher cost because of the additional IR channel and additional complexity in the detector. So these kind of detectors are normally used in the case of the complex fire environment where there is a chance of burning of multiple different components and there are various different spectrum available. Multi-IR detectors have gained significant traction in the market due to their enhanced detection capabilities and reduced false alarm rates. This detector typically relies on CO2 IR band at 4.4 micron and additionally H2O IR band at 2.9 microns, detecting specific type of fires such as ammonia or hydrogen fires. Multi-IR detector offer longer ranges and are resistant to signal attenuation caused by oily vapors, fumes, and other interference sources like welding arcs or lightning. By employing three IR sensors, each tuned to a different spectral band, this detector can achieve a detection range of 40 to 80 meters for standard heptane fires, even in the environments with multiple IR interfering sources. So this is a major improvement here. And so here I am writing like three IR sensors, but in the market there are multi-IR detectors which have four IR sensor or even more. With respect to the advantages, first advantage is long detection range, as we have seen that they are able to cover 40 to 80 meter. That is advantage number one. Second is low false alarm rate. These detectors are designed to be highly sensitive, significantly reducing the occurrence of false alarms even in challenging environments. And resilience to interference. Multi-IR detectors are less affected by signal attenuation due to oil vapors, fumes, and other interfering sources like lightning and welding arcs. With respect to disadvantage, the complexity and cost is higher because here we have three or more IR sensors. Specialized application. While effective, these detectors are often tailored to meet specific fire types and environment, limiting their versatility compared to their or other options. So these detectors are sometimes specifically designed for hydrogen and sometimes specifically designed for hydrocarbon fire. So there are different model for hydrogen and hydrocarbon fire. So that limits its versatility. One detector cannot be used for and both fire from hydrogen and hydrocarbon. So there are some limitation with respect to the multi-IR detector also. Placement of fire detectors are of major concern. If we cannot place the fire detector properly, they will not be able to detect the fire. In chemical and refineries, the fire detectors are mostly placed around the hazardous areas, like in and around of the storage tanks, near the valve manifolds and the transmission lines, near the critical equipment like pump, compressor, etc. While placing a fire detector, mainly two things should be kept in mind. One, there should be a clear line of sight between the detector and the fire, and the distance between the fire and detector should be within the acceptable range of the fire detector. From a geometrical standpoint, the amount of signal received by a detector from the fire reduces as the square of the distance between them, right? So the intensity of the fire that is received by a detector is inversely proportional to the from the distance, right? From the square of the distance. Because the surface area is getting decreased, the viewing angle is getting decreased, and this is the formula that is normally used. So if you have a detector at a distance d1 and after some time the distance gets changed to d2, the surface area gets changed from s1 to s2. So you can, if you know s1, then you can know s2 by knowing d1, d2 and s1.